Welcome back. This is the third video in class 17 in thermodynamics. In the previous one, I talked about heat engines and efficiency and the coefficient of performance. Here were some more figures from Sengel, where they're showing here, for instance, is what we were describing as a heat pump, where we're taking heat from the outdoors, even though it's cold, but we're using this device, and they're showing the labeling a coefficient of performance 3.5. We're using work in to a compressor in order to reject the heat into the indoors. So even though we're moving once again from a cold to a hot, but we have to have this mechanical device inside. And they have labeled this the coefficient of performance. We have desired output, the required input, what you want over what you paid for. QL, which is the low thing, that we want this low, we want to move the heat away from our bologna here and put it to the back of the refrigerator. And so that's why we have this QL divided by work net in, as opposed to the heat pump where we have the cold environment outside and we're rejecting heat into the house, which is what we want. So that's the desired output. So what you want over what you paid for, and that's a coefficient of performance. And both of these are values that are generally, I think almost always, going to be greater than 1, as opposed to efficiency, which is always less than 1. This was funny, so I saw this was in Sengel, kind of funny, Blondie, and this is Dagwood. If you've ever heard of a Dagwood sandwich, he used to make big sandwiches, so in the thing, or maybe he was named for the sandwich, I don't know. So anyway, honey, are you air conditioning the outdoors? No, I'm heating the house, which is what a heat pump is. Okay, so here's an example from Brorgnacki, and this automobile produces 136 horsepower, and I'm using American horsepower instead of the European horsepower. It's a weirdness that there's just a little different. On the output shaft, with a thermal efficiency of 30%, the fuel burns gives off 35,000 kilojoules per kilogram as energy release, which, by the way, doesn't agree with most places, I think, in the amount of fuel heat, in gasoline. But anyway, find the total rate of energy rejected to the ambient and the rate of fuel consumption in kilograms per second. Well, personally, what I would like in looking at this is numbers that I'm familiar with. So I'm going to adapt this example. I also have a similar example from Sengel that's going to be in several videos from now, where I think that the numbers are make a little bit more sense. We use US units. But I'll make the conversion anyway. So anyway, here's we have atmospheric air is coming in, and the source in this case is going to be the fuel, right? And then the sink is going to be like the exhaust right here. But some of the sink is also going to be the atmospheric air, the coolant flow coming out of the radiator. There's different heat rejections, but the power is going to come out through the shaft work. So let's try to do this problem. All right, we're going to get more light in here. I'm putting a light onto there, but sometimes it makes these weird lines. All right, well, we'll just have to live with it. Okay, so let's start out with the power. Well, they gave us in horsepower, so I'm going to turn it into kilowatts because they gave us kilojoules per kilogram. If you look at the back of the book, now this is the US conversion. There is in the back of the book a conversion that's slightly different for European power. I don't know why they're using it. So I'm going to say, if I hear a horsepower, I'm thinking it's American horsepower. All right, so here you go. Here's that many kilowatts. This number should become familiar with you, 0.746 often, like 75% right there. And now QH, though. All right, so the amount, so if the efficiency is this, remember, the efficiency is that right there. That's the out right here. So this is the output. So we want to get this. So we have to divide by the efficiency. That's an eta. Looks really sweet, doesn't it? Make a nice looking eta. 101.4 divided by 0.3 because it's 30%, and we get 338.1 kilowatts. And they want to know, well, what is the, well, first off, they want to know what the rejected to ambient. How much is rejected ambient? And that could be from the ambient air coming through the radiator, but also the exhaust flow. Y'all, it's rejected heat. And so you could take, if we want to find that, right, we could say that the Q low is going to be equal to the Q high minus work rate. So these is just another way of keeping track of energy. All right, so it's really sort of a first law thing, right? 338, it is a first law thing. Minus 101.4, and so we get 236.7 kilowatts, which I guess is interesting. I don't know. What does that tell you? Well, we lose a lot more heat than we actually are able to convert. But you kind of knew that from the 30%, right? That was kind of already told, but it's just quantifying it. They told us that the heat content, so it's per mass, is 35,000 kilojoules per kilogram. I looked up on the internet, and it says that the heating value of fuel in SI units is usually, of gasoline at least, is like 44,000 to 46,000. So it's a little on the low side. If we want to find out what the mass flow is, we'll just remember that we could find the big H by taking the mass flow, multiplying it by this per mass heat. Therefore, we could find the mass flow by dividing the heat rate by the heat content per mass. So 338.1 divided by 35,000 is going to be equal to 0.00966 kilograms per second. And so that's the answer that they're generating. But I'm all like, so what? I don't know how much a kilogram per second. Is that a lot? Is that a little bit? But I do know how much mileage my car gets. It's not a lot, because I should get a better car. And we know that's going to be typically measured. We want miles per gallon. Sorry, miles per gallon. And how do we get miles per gallon? Well, we have a rate right here, but that's in kilograms per second. But what if we got this into gallons per hour? What does that do for us? Well, what we could do is we get miles per hour and divide it by gallons per hour, right? And those hours against it, and then we would get miles per gallon. So we have to make an assumption. They told us this thing was 136 horsepower. Now, we're going to want to try to do this at a constant speed or an average speed. To tell you the truth, that's a heck of a lot. That is a lot of power for a constant speed automobile. I mean, that's a ton, a whole lot. This is like big time truck kind of amount of power. Now, an engine, of course, your car engine has, unless you're like my little Honda, can often have a lot more power than that. But it's not using that power while it's running down the road at 65 miles per hour. But let's go, okay, well, what if it did? What if it did? So that we want to try to get sort of a range. We're just trying to get our head around how much is this? So what if that power, what if 135, if the power was equal to 136 horsepower at 65 miles per hour, because we don't want to go over the speed limit, do we? Never mind. So let's, okay, so I have 65 miles per hour for this. I want to turn that into gallons per hour just so I can rationalize things. So I went ahead and found out that 1 gallon of gas is approximately 2.838 kilograms. So that's 2.838 kilograms per gallon of gas. right? So now I can turn that, and then I can turn this into seconds, right? I can turn that into hours. So what I could do is I could take, I'll call it this right here. This our volumetric flow is going to be our 0.00966 kilograms per second. And this, by the way, this conversion has a density conversion into it, right? So I could take 3,600 seconds per hour, and then I could also take and divide 1 gallon by 202.838. And so my volumetric flow is going to be 12.25 gallons per hour, which seems like a lot. I mean, that's a lot. I mean, you know, I have like a, I think I have a 20-gallon tank. So that's like, I would take me, I would have to get gas more than twice, you know, every other hour at least, right? But anyway, miles per gallon is going to be that 65 miles per hour divided by 12.25 gallons per hour, which ends up being 5.31 miles per gallon. Kind of redundant right there. But anyway, that gives you sort of an idea, right? Now my Honda Pilot right now gets 20 miles a gallon. That's terrible. I know it's terrible. But I used to be able to get 65 miles a gallon in my Civic, my Honda Civic. I like Hondas. But I can't put band equipment into a smaller car. And we also live in New England where the snow will, you know, try to throw you off the side of the road. So you need a 4-wheel drive, all-wheel drive. And also I can fit like, I know, I'm rationalizing, but I can fit like 6 adult males in my, you know, we have the extra row in the Honda Pilot. So I know I should get a more efficient car. Maybe I will. We'll see. Anyway, that was a video at 12 minutes. I have a very, very short example in the next one for a refrigerator. It's almost silly to make it into a separate video, but I'm gonna. So let's see a coefficient of performance in the next video.